Hi everyone, my name is Michael Snoyman. I'm going to be speaking today about server-client hybrid web applications using Haskell. This is PolyConf, so obviously the question is, how do we get Haskell that's running on a server to talk to a web browser that is clearly in some form or another running JavaScript? Let's talk a little bit about Haskell first. So most of you have probably heard of Haskell. At the very least you heard it today because it was mentioned a few times. So Haskell is a strong, statically typed language. It's got an asynchronous I/O manager, which makes it very powerful for concurrency. You're basically able to write code that looks like it's blocking, but is actually using an invented system under the surface, which is very convenient for example, writing high-performance web servers. It's got green threads, so that when you do a fork, it's not actually creating a system thread, it's doing a thread inside the runtime system, which is much cheaper. And Haskell has a very large number of practical libraries that we would love to be able to take advantage of all over the place. Those are the features of Haskell that we're going to focus on today for the purposes of what we can do on the client side. And on the server side, we're going to be using the Yesod web framework. I'm the lead developer of that framework. Yesod, for people who aren't familiar with it, it's just basically a standard MVC framework like many other web frameworks. The difference being that it tries to take advantage of the features of Haskell, mostly about the type system. Being able to prevent things at compile time instead of waiting till runtime for things to break. What we want to be able to do is get those exact same advantages on the client side. So to start off, let's look at the simplest example of how it is that we could do a web application that has some JavaScript running. So up here, we're using Hamlet, which is the templating system that we use in Yesod for HTML. And we're just going to generate some HTML. You can probably guess what that looks like, even though you've probably never seen Hamlet before. And then we're just going to point to this external JavaScript file. We're not actually integrating these two things at all. There's some Haskell code. There's some JavaScript code. We're going to embed a link to the JavaScript code. Very common, very straightforward, very low level. And this is the code, and it's straight JavaScript. At this level, there's really no integration at all between the code base of Haskell and JavaScript. We get no guarantees, we get no nothing. So you can do this, but it's kind of boring. So let's try to spice it up a bit. The next level above that also isn't too terribly interesting. Instead of pointing to an external JavaScript file, we're going to let the Haskell server process the JavaScript and serve it. But it's not actually going to do anything interesting with it. It's just taking the exact same code. That, again, is not interesting. This is where it starts to get interesting, but it's still pretty boring. Instead of just taking some code and throwing it out at the web browser, we're actually going to do some variable interpolation. So now we're starting to see how we could get these things to play together a little bit. We can actually share this identifier that we generated there and share the exact same identifier for both the HTML that's generated by the server and the JavaScript that's going to run on the client. Nice thing about this is we can make sure that there are no name collisions, and we can make sure that there's no, we didn't accidentally mistype the variable name. That's nice. But it doesn't really do very much. We haven't actually prevented any kind of syntax errors. You could put over here, if I, for example, left off the parentheses there, nothing's going to stop that from compiling. So instead, let's talk about some syntax checking. Everything we used until now was something called Julius, which is an unchecked version of JavaScript. We could also, for example, use CoffeeScript, which there's built-in support for in Yesod. And in the case of CoffeeScript, it's actually going to pass that off to the CoffeeScript compiler. And if there are any problems compiling it, that will be caught at the Haskell compile time as opposed to later on, which is closer to what we were looking for. You could theoretically say that it's really nice that Julius doesn't do any syntax checking because you can do this, but I've never seen that and it looks like an abomination to me. So I wouldn't recommend it. That's great, but I started off not talking about syntax. I started off talking about the type system. We still don't have any type checking. So this is perfectly valid syntactic JavaScript code embedded inside Julius. We're going to take an integer, we're going to take a string, and we're going to add them together. And of course, it does exactly what JavaScript does best, which is the wrong thing. So it's going to go ahead and generate one TWO, which I don't think anyone really wanted. If you really wanted it, I disagree. So I happen to be a big fan of the WAT talk, which I'm sure many of you have heard. If you haven't, go listen to it because it's hilarious. So you get the reference if you've seen that. So the point is, we want to be able to do something more intelligent on the client side. So everything we did until now was just taking JavaScript or CoffeeScript, which neither one of them are type checked, and running them on the client. Why don't we talk about a nicer language on the client side? So there are a whole bunch of nice languages that are coming out: TypeScript, LiveScript, others you may not have heard of, Roy and Elm. These are great client-side languages that have some type checking. Beautiful. Why don't we go ahead and embed those? Except I told you this was a talk about Haskell. So why don't we just use Haskell on the client side? It turns out that there are currently 3 popular options in the Haskell world for how to compile your Haskell code into JavaScript. GHC.js is by far the most advanced. GHC is the flagship Haskell compiler. It has many, many features. And in particular, it has all those features that I told you about at the beginning. A very powerful type system, and it's got very nice concurrency. So GHC.js goes ahead and ties into GHC, lets it do all of its, its parsing, most of its code generation, and then right before it actually spits out native code, it takes that last representation, which we call core, and turns that core into JavaScript. It also implements the full GHC runtime system in JavaScript. So anything you can do with GHC code, you can do in GHC.js. You can get threads, so even though JavaScript code is actually going to be running in a single thread inside the browser, you can fork and run multiple threads when you use GHC.js code. You can throw async exceptions, which means that you could, for example, let some computation run for 2 seconds and then kill it if it's not done yet. And you get software transactional memory, which I'll give a nice example of later. If you haven't used it before, STM is a great way to avoid race conditions, deadlocks, and a lot of other problems that we run into commonly. Fei is the simplest of these 3 options. Fei uses a Haskell parser, but only really deals with a subset of the language. It doesn't do anything about the runtime system. It basically has full semantics of JavaScript at runtime. It's just using Haskell for the syntax and to do some type checking. One of the nice advantages of Fei, on the other hand, is that since it's so close to JavaScript, it's very easy to do the FFI, which is foreign function interface, to be able to call out to JavaScript. The third compiler, which I'm not going to talk about today, is Haste, which falls in between the 2 of them. I simply don't have as much experience with that, so I'd like to leave it off of the talk today. I also only have 30 minutes. All right, so first example we want to talk about is communicating with the server. This is a common problem. We've gone ahead and we've written something on the server. It's providing some kind of an API. We want the client to be able to call it. We want to make sure that it's calling it correctly. So how do you do that? The way that we do it in this setup is we declare some Haskell data types that will be shared between the client and server-side code. Those data types will essentially state an RPC framework to be used, and the only way that you can make a call to the server is by creating one of these values. Once we're doing that, we get to use all of the normal tricks that we use in Haskell, like new type wrappers, which if you don't know what that is, that's fine, you'll see in a moment. We get to use all those standard techniques to make sure that this thing is safe. So we'll start off with Fei. We're going to put together a very simplistic blog application where you're able to go ahead, create new blog posts, and then request those blog posts. There's no security, there's no nothing else. It's very dumb. We're going to represent each post by an integer. But we don't want to just start throwing integers around the internet. We want them to be typed. We want to make sure that we're not accidentally using someone's age as a blog post ID. That would be stupid. So we've gone ahead and we've wrapped that up, and this is now a new type that can't be replaced with a normal integer. Similarly, we're going to have a title and the actual content for each one of these blog posts. We don't want to accidentally swap those 2 things and mix them up. So we've wrapped those 2 things up in new type wrappers as well. And down here, we're actually defining what our API looks like. So we have a command. One command is add post. When you want to add a new post, you have to give it a title and a content, and it returns back to you a post ID. Similarly, if you want to get posts, you don't actually have to provide it any more information. It'll give you back a list of the post ID together with its title, and you can also request the content of a specific post. This is just here to satisfy the type system, basically, to allow the type system to check what it is that we're returning back. This is what we call in Haskell a phantom data type. Also in Fei, I mentioned that we have a very lightweight FFI. So this is just a wrapper around jQuery. We're able to do things like wrap the getVal function, or the val function, And we call it getVal because we're using the getting aspect of it, if you're familiar with jQuery. This thing right here, the %1, that's simply going to embed the reference to the jQuery object. That's a very simple way to call out to the foreign code, to the JavaScript code in this case. It's one of the nice advantages of Fate. It's very easy to take the huge number of existing JavaScript libraries and just use them. And then we get to throw this all together. So this is what the actual code looks like for the example that's running on that website that was referenced earlier, and I'll show the link on the last slide again. We want to bind to the click handler event on the add post button. And this right here is what we call a lambda. This is also known as a callback. So we're providing an anonymous function, which is going to be provided with an event. And this is going to be run every single time we get that click. We're going to prevent default, same thing that you would do in jQuery. We're able to set the text. Important thing is that we have this function call that will go ahead and use the command that we defined previously. And then the results are guaranteed to match the results in the RPC. You're also guaranteed that you can't accidentally mess up the arguments. If you put the content before the title, it wouldn't type check. If the server changes its API, and now it also takes a date in addition to the title and content, you try to compile your code, it won't type check. So again, we're preventing things from being runtime problems, now they're compile time problems. Other notes on Fay. It is Haskell syntax, but it's not all of Haskell. Things like type classes aren't there, gaddits aren't there. A lot of the things we would like to use simply aren't supported. And it runs like JavaScript. So that's the simple version. Now we're going to have more fun. More fun is playing around with GHC.js. As I said, this thing can do everything that GHC can do. It also works in a very funny way, in one specific manner. It uses all of the same libraries that are used on the server on the client. So even though JavaScript has built-in support for text and JSON, we're actually going to use the Haskell libraries for text and JSON inside the JavaScript, the compiled JavaScript that's running on the client. That might seem a little bit weird, but it means that we're going to get identical behavior between what's going on the server and the client. The most important reason for this is that when we do our serialization of data across the network, we're going to have the exact same serialization, the automatic generated serialization that ASON provides, our JSON library, both on the client and the server so that we don't get any kind of mix-ups between the way that things are serialized. Also, the text data type in Haskell is actually more powerful than the JavaScript string data type, so we get a few more features from there. And as we'll get into, we also have a totally different threading model. So I mentioned that callback, that Lambda thing before. Notice how when I did this call, I had to provide it with a callback. We don't do that in GHC.js. We're going to go ahead and make a call to the server. We're going to say, hey, give me the content, and we're just going to get it. We're not going to say, hey, by the way, when it's done, please call me back. We're just going to pretend like that blocks until the data is available from the server. Anyone who's dealt with writing JavaScript server-side code is probably cringing right now. You can't do that. That's terrible. That's horrible. It's going to destroy all asynchronicity. It's going to be terrible. Guess what? Under the surface, this code is essentially being converted into this code. So you don't have to deal with callback hell. You don't have to deal with the deeper and deeper nesting of things being called back. You just get to write this very simple code and say, I'm going to pretend like things are blocking, even though they're not. In this kind of an example, it's basically syntactic sugar. It doesn't mean very much. But once you start doing more complex things, the difference between these two worlds is night and day. So this is a huge boon to productivity. Another example, let's say we want to do some debouncing. So the user is going to have a button on the web page. We want to let them click it and perform some kind of an action. But if the user clicks it more than once per second, we want to treat it as a single click. Common use case. This is how we would do it in GHC.js. We've created an mvar. An mvar is a mutable concurrent variable. And it's going to be our signal. And now we're going to create a new thread. This is going to be a green thread. And it's just going to loop forever. And every single time it's going to block waiting for the signal to be fired. When the signal is fired, then we're going to get the current time, spit it out. That's just some boring stuff that I put in there, but you do something more interesting. And then we do this thread delay at the bottom, and that's in microseconds. So it's 100,000, meaning 1 second. Sorry, a million. I'm sure someone's laughing at me right now. So it's a million microseconds. The point is, if this signal gets fired multiple times, it's only actually going to this is only going to get triggered once. Every single time you trigger the signal, it's going to be ready the next time you want to take this value. But if you do it twice, you're safe. So this is very simple, straightforward debouncing code. Now let's talk about software transactional memory, STM. STM is a different way of dealing with shared mutable state in a concurrent model. So the standard approach is you'd want to go ahead and you'd want to get some kind of a semaphore or mutex you want to block. We don't do that in STM. We just kind of write the simple code that you would expect would work, and it takes care of things behind the scenes. It notices, sorry, someone else modified that variable while you were looking at it, let's try again. This is, if you want to get into Haskell advocacy, this is why purity is a good thing. It allows us to do these kinds of things, but that's not what I'm talking about right now. So anyway, this is going to be the first part of our STM. We just want to display the balance on the screen. So we have these two spans, Alice and Bob. I'm going to grab them from jQuery, and we're going to have this loop. And in this loop, we're going to set the text for each of these spans to the current value of Alice and Bob's bank account balances. And then we're going to enter this STM block. That's what atomically does. We're going to look at the two variables in their current state, and we're going to check that either Alice's new value is not equal to her old value, or Bob's new value isn't equal to Bob's old value. If both of those values are the same, we're just going to block and wait for one of them to change. This is exactly the semantics we want when we want to go out and update things on a web page. We want to just get a signal that, hey, by the way, things have changed, let's go out and update it. This is all going to go on in a separate thread. You'll see that at the end, we're calling fork.io. That thread will block, and because of the way that the GHC runtime system works, that thread will just go to sleep. And other threads will run until this thread is ready to be worked on. Next thing, we want to go ahead and pay Alice every, did I get 5 seconds? Yeah. Every 5 seconds, we want to go ahead and pay Alice. So you might be worried, well, maybe we need to worry about some kind of interaction with the previous code. Maybe there's going to be a race condition. There's not. STM guarantees that there aren't any race conditions here. All we're going to do is forever wait 5 seconds, and then give her an extra $10. Euros, I don't care, whatever currency you want to talk about, shekels in my case. So you just go ahead and pay her every 5 seconds, and that just works. We're also going to provide this function called to give Bob $5 out of Alice's bank account. And that'll just be a button that's on the web page that the user can click. We ask for Alice's bank balance, we check that she actually has enough money to give the money to Bob, and then we write these. And again, people who are used to normal concurrent programming are probably cringing and saying, no, 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 this is terrible. What happens if Alice's bank balance was modified between these two things? This thing is going to be terrible and it's going to destroy it. No, that's not the case. STM says that if Alice's balance was modified between here and here, then the entire transaction is invalidated and we start over from the beginning. So this will just go ahead and make sure we have full access to control all of the variables that are touched, and only after all of that is the transaction actually committed. Finally, this is the way that we run the whole thing. We start off Alice and Bob at both $100. We get this jQuery button, and we bind a click event handler to give the money to Bob. And then concurrently, which is a really cool feature from the async library in Haskell, we concurrently both pay Alice every 5 seconds and make sure that we update the balance. We don't have to worry about any, behind the scenes, this is going ahead and forking, and it's making sure that these two things run at the same time. You don't have to worry about that. You can just use this kind of high-level combinator from the async library called Concurrent, called Concurrently. If you're interested in Haskell concurrency, I strongly, strongly recommend looking at the async library written by Simon Marlowe, who also wrote a book on concurrency and parallelism. Whole thing is very cool. Lots of great ideas in there. So, more things in general about GHC.js. Full-powered Haskell, like I said, both in the type system and the runtime system. you can access basically any library that exists today for server-side code, which is kind of magical. So the debounce example that I gave you, originally this slide actually used code that's used in my web server to debounce grabbing new date values. Or, sorry, that one was actually for flushing to the log. Point being that there was this general purpose library that did something that was very important, very high performance. It was written properly on the server. We can just take it and use it on the client. That applies to things like text. It applies to all across the board. The one big exception is any of the Haskell libraries that use the CFFI aren't going to work, which kind of makes sense because we're not able to run C code in the browser. I'm sure someone is thinking, why don't you just use Emscripten and compile it? I'm sure someone's going to do it one day. We just haven't done it yet. I look forward to that day. That'll be a lot of fun and terrifying. The other really cool thing that I want to point out about playing with JS is it's fun. Myself, a coworker of mine, Chris Dunn, we started playing around with this. It's kind of hard to put it down. Once you have access to all of this cool server-side code that you've been playing around with, getting to play with it on the client also just opens up a whole bunch of opportunities. There are downsides that I have to mention. First one is that the code size of GHCJS generated code is larger. Not necessarily very much larger. The experiments that we did came out with a full-powered application after minification and gzipping at 300K, which is large but not terrible. Basically the size of a large image, so it's not really going to affect the download speed of your application too much. I wouldn't recommend using this for a little tiny script on a page, but if you're writing a full-powered web application, I would definitely give GHCJS a shot. The installation procedure is actually a little bit complicated right now. We're working on that. My company, FP Complete, we're probably going to be coming out with some tools to make it much easier to get started with GHCJS. Another one is, and actually specifically because of the previous point, since it's been complicated to get started, not as many people have started jumping into it yet. We're hoping to kill that problem by making it easier, but in the meanwhile, there hasn't been as much testing done, so you're more likely to run into some kind of a bug. Hopefully that won't be the case. I don't have enough real-world experience to tell you how likely that is. And the FFI layer is a little bit more complicated. Like I mentioned, we actually use the Haskell text data type instead of the JavaScript string data type. So when you go ahead and call out to JavaScript code, you actually have to do a conversion in between. You might be worried about performance. The performance of GHCJS is actually pretty competitive. It is in the language benchmark shootouts. You can go ahead and check out some of the things there. I actually did have a slide demonstrating the FFI. So you can see we have to convert the text value from Haskell into a JavaScript string value, a JS string is what we call it, before you're able to use it. So it's a little bit more verbose than the FFI, but it's not too terrible. One of the nice advantages of all this is that when you have different semantics in what the data types mean, you get the Haskell version. So for example, anyone who's ever played around with large numbers in JavaScript knows that since even integers are actually represented as floating point numbers, you only get about 52 bits of precision when you start dealing with numbers. If you use GHCJS, that's not the case. You can go ahead and use the integer data type, which is arbitrary precision. You can use the int64, which gives exactly 64 bits of precision, and you'll get exactly the same behavior as you would get on the server. So, in conclusion, you have a full spectrum of what you're able to do when you write web applications in Haskell. Anything from writing everything completely in JavaScript without ever going through Haskell to you never wrote a line of JavaScript and everything you ever did was in Haskell. You can pick many, many points on that spectrum wherever you want to go. What's going to guide that decision is all the different trade-offs that we talked about. I would definitely, my focus usually is on type safety because I care quite a bit about making web applications or applications in general that work and are robust. So that's my focus. The simplicity of doing concurrency is also very important. You also have to keep inside some of the downsides, like the code size. You can go to this URL to go ahead and play with the application. And this is the minified version of the link to the code itself. Okay. Any questions?
Hello. A question about bindings to certain browser APIs. I know you can do arbitrary FFI to JavaScript, but are there any libraries that you know of for doing, maybe calling local storage or some of the browser like touch APIs?
I don't know about local storage and touch. What I do know is that there's a project, a working project, that takes the DOM specification and auto-generates a full FFI binding to it on a regular, it's something like 113 modules, it's massive, but it has every single possible function already pre-bound. There's a jQuery library, there are a few others. I haven't dived into this deeply enough myself yet to know exactly what's out there in the ecosystem, but it's probably not too hard to write these wrappers, and if you talk with the community, it's probably something you could convince someone to help you out with.
So how painful the debugging is?
So the one bug that I ran into while working on GHC.js here was a compiler bug, and it gave it essentially said invalid closure type, and I had no idea what to do about that. So that was pretty painful. The guy who's been working on GHC.js is incredibly responsive. He took care of it, I think, within 12 hours. So if you run into those kinds of things, it's going to be intimidating. But there's plenty of support, and there are other people in the community also who are happy to pitch in. The community wants to make sure this works, so you will find people who are able to help you. Once you get past those kinds of compiler bugs, just normal debugging is going to be the same thing as Haskell. So you've got almost all the same tools that you have from Haskell in general.
So have you seen or have any experience with PureScript? It's another thing that could be interesting.
I've seen it. I don't have very much experience with it. It's another one of those things that falls on that spectrum. I think just yesterday someone was telling me about PureScript being an option when the GHC.js runtime overhead was too high. So yeah, it's definitely another thing that you can consider. Personally, I like the idea of going full-blown with Haskell, but if you're not necessarily invested in that, PureScript could be a great option.
So actually, as far as I know, the difference is that it tries to compile into more idiomatic JavaScript code, so it has the semantics of JavaScript, so the code should be smaller. But the syntax is a bit different, and it's not even a subset of Haskell, I think.
Right, so I'm saying if you actually just want the semantics of JavaScript, then I'd recommend going with Fay. So Fay is something that I actually have used in production. FB Complete's web-based IDE is written almost entirely in Fay. So we've been working on it for 2 years. That's definitely production quality. I can't give you a comparison of Fay versus PureScript. I would check both of them out and see which one of them you like more. Is that it? Okay. Thank you very. Oh, sorry. One more.
Hi. So you mentioned it's used on production.
Yeah.
So are there any implementation on production for really high traffic projects or products?
Are you talking about GH? So what I was saying we use in production is Fay. So Fay, the FP Haskell Center, the web-based IDE, our School of Haskell, all of those projects are written in Fay. There are a number of other websites. I don't know them offhand, but those things are written in Fay. I am not aware of any production website that's written using GHC.js. It's possible that they exist. There are definitely a lot of demos out there. But I don't know if there's anything that, there's any industrial strength implementation of GHC.js running. I could be mistaken, but I don't think it's hit that yet.
Thanks.
Sure. One more?
Last one.
Do you also build Cabal packages for GHC.js separately from the Cabal packages that you would use on the server?
Yes, if I understand the question, so when you're using GHC.js, an explanation for everyone else. So Cabal is the package manager that we use in Haskell. Every individual package that gets uploaded is in Cabal format, and then you use a tool called Cabal as well. Use Cabal to go ahead and download those and install them. GHC maintains a package database of all the binary versions of these because it compiles everything in advance into machine code. When you're dealing with GHC.js, what you do is you have a modified version of Cabal that has the ability to target GHC.js instead. GHC.js has its own package database, where instead of machine code, it has JavaScript code that's been generated. And therefore, if you want to go ahead and say install the foo package, for lack of a better idea, you want to install the foo package, you would go ahead and do cabal install --GHC.js foo. And then you'll go ahead and get that in your GHC.js package database. Important would be you want to make sure that you're using the same version of the package both in GHC and GHC.js so that you don't get some kind of weird mismatch between the two of them. And if you want tooling on that, that's exactly the kind of thing we're working on right now. Okay, thank you very much, everyone.